if we have a chunk of an element, is it going to have a lot of atoms or just a few atoms? A lot. It's going to have a lot of atoms in it because they're teeny tiny. And so we hinted around this when we talked about mass, and average atomic mass, that we said it's not terribly practical to talk about the mass of an atom on the scale of times 10 to the negative 25th kilograms. It's just a really small number. And so what we're going to learn about in this lesson is a counting number called the mole. So you are already familiar with a counting number, at least one. If I have 1 dozen pencils, how many pencils do I have? 12. If I have, 1 dozen. If I have 1 dozen students, how many students do I have? 12. It doesn't matter what I'm counting. 1 dozen is 12 things, right?
Why is the baker's dozen 13?
Huh?
Why is the baker's dozen 13?
I don't know.
So they can eat one.
Okay. So we have a counting number, and that is 1 mole. So 1 mole is 6.022 times 10 to the 23rd. So is that a big number or a small number? Big. It's a very, very big number. Does it make sense that if we're talking about atoms, I don't know why that came up, and parts of atoms, this is a very big number? Yes, why?
Oh, because atoms can fit into it.
Because we're counting things that are so small. So if you look, I've written this ending of things, just like 1 dozen. 1 dozen is 12, whatever you're counting, right? 1 mole is the same way. 1 mole is 6.022 times 10 to the 23rd of anything. So what we're going to use moles to count are atoms, ions, isotopes, then parts of atoms, so protons, neutrons, electrons, and then we will get to molecules and formula units when we talk about bonding.
Can that change? Like, it's just 1 mole with 6.22, that number doesn't change?
Nope.
Never changes. So it
is 6.12, is that like the average?
It's not. It is, and I looked this up not that long ago. It has something to do with gases like it's the number of gases under certain conditions. It's just set to be like a dozen. It doesn't matter what you're counting. It's just a way to represent it.
So if you're saying that there's a mole of atoms, there's that many atoms?
Yes. Now, where kids, I think, struggle with this is, and if you take it back to a dozen, it'll make sense. If I have 1 dozen pencils, they would all fit on the top of that desk easily, right? If I have 1 dozen students, would they all fit on the top of that desk easily? No. So 1 dozen doesn't really give us an idea of the size, right? I could have 1 dozen paper clips and 1 dozen bowling balls, and they would be different sizes, different masses, different weights, different densities, different volumes. The same thing is true for the mole. It depends on what you're counting. But when we say 1 mole, that is 6.022 times 10 to the 23rd of whatever we're counting. Okay? So if you find yourself just like, just remind yourself it's a counting number. Okay? So that's one of our new conversion factors. The other new conversion factor that we're going to talk about is molar mass. And you actually already know a lot about the numerical value for molar mass, because it's the same numerically as average atomic mass. We just add a different unit to it. Okay? The next part you don't have to write down. You obviously get a choice in whatever you want to write down anytime we go over it, but this is just to give us a little bit of context for macroscopic things, things we can see with our eyes, and if we had a mole of them, how big would it be? So if we had 1 mole of Coke cans, how many Coke cans would that be?
6.02 times 10 to the 23rd.
Okay, a lot, right? They would cover the entire surface of the earth at a depth of 200 miles.
So does that mean like they'd be up 200 miles?
Yes, the whole surface of the earth would be covered in Coke cans 200 miles deep. So is it practical to count Coke cans with a mole? No. Could you still do it? Sure. It's just not as useful, right?
Could you use it for specks of dust?
You could. Popcorn kernel, unpopped popcorn kernel, about the size of your pinky, right? Smaller than a Coke can. If you had 1 mole of popcorn kernels, they would cover the entire surface of the United States at a depth of 9 miles. So is it practical to count popcorn kernels with a mole? No. Could you still? Yes, it is a counting number. We could count atoms with a dozen. It's just not that practical because atoms are so small. If you wanted to count 1 mole, or 6.022 times 10 to the 23rd, if you counted at a rate of 10 million per second, it would still take 2 billion years to count. It's a very, very big number because we use it in the most practical sense to count really, really small things.
So, like, what is an example of a mole? Like, in like this, or?
That's
Wait,
a
what's
very
the
good
number?
question.
Like, what's the number? What's 2 to the 23rd? Is that like a number name?
Cajillion, Badillion, I don't know. I don't think, it probably does have a name.
I'm gonna look that up.
I am unaware of it. Okay, so each of these, I'm gonna let you hold these. Then we're all gonna wash our hands afterwards, okay? So this, let's see if I can do this. This is 1 mole of aluminum. So I'm gonna, let's see what's gonna do this.
1 mole.
This rectangular prism is 1 mole of aluminum.
Dang.
So it's got a mass of about 26 grams.
So, wait, so 1 mole of aluminum, is that like, what pieces of aluminum? What?
Aluminum metal?
Yeah. Wait, so, I'm confused. Wait, so is there 1 mole of aluminum atoms?
Yes.
And, okay, that makes sense.
The next one I'm going to put up is 1 mole of copper. And I'm going to have you come around and pick these up if you feel comfortable, because you'll be able to feel the mass difference and look at the size. The next one is 1 mole of zinc. And then this is 1 mole of lead. I'm pretty sure. We'll pretend it's lead. I'm pretty sure it's lead. We could figure it out if I found the mass. It's not lead. 65, 63. Iron. This is 1 mole of iron. So if you want to, you can come and feel these. You can pick them up, but then you need to wash your hands right after you do it. Pick it up.
I'm trying to figure out the. Aluminum.
Copper. Zinc. What did I say? Iron.
Would like the density and the weight, like, be based on its number?
Yes, the density depends on how tightly the atoms are packed together. Copper. Lead. No, iron. 1. Zinc. And I'll leave them out here. You can come feel them. Just make sure you wash your hands thoroughly afterwards. Not that people would lick them, but
Oh,
So the first one, determine the number of atoms in 0.500 moles of aluminum. So what are we given?
the amount of mole.
We're given the moles of aluminum. So let's start. We want the number, the unit. And what are we asked to find?
Half.
The number of atoms. So we have a new conversion factor that allows us to convert between moles and atoms. And that's Avogadro's number, right? We know that 1 mole of a substance is equal to how many atoms? So how are we going to plug that conversion factor into our T table to make the units work out? One mole on the top or bottom?
Bottom.
Why?
Let's go diagonal. So you can cancel it out.
So moles cancel out. And then what that's equal to goes on the top. So 6.022 and 23rd. Okay, like I said, moles cancel out and we're left with atoms, so we're ready to type it into our calculator. You need to practice using your calculator, either your phone or your calculator that you use, because when you have to be careful with plugging numbers in scientific notation. You need to tell your calculator, either put the entire number in scientific notation in parentheses, use second EE. Otherwise, there'll be times where you end up with order of operations issues. Let's review significant figures. So is Avogadro's number going to affect significant figures? No. Conversion factors don't affect sig figs. So what am I going to look at to determine the number of significant figures? And how many significant figures does it have? How many? I can't hear you. 3. So the 0.500 has 3 sig figs. So our answer should also have 3. So when you tippity typed it into your calculator, what did you get?
My calculator's not working.
Why is your calculator not working?
I have no idea why. I really don't.
You can do this in your head because you're just dividing by 2, right?
So
What do you get?
3.011.
3, so 3.01.
It will not be 11.
No, that's 4 sig figs.
Oh, yeah. I was trying to-
Yep. Good. What?
There's 4 in the.
There's 3 in 5.00.
I was confused. I was thinking about the.
What's it say, because the last 2 are just placeholders, and you have the decimal, but you don't count the first one, you don't stop and keep starting.
These 2 zeros aren't placeholder
Is
zeros.
there after the decimal?
Yeah.
Yeah. Yes, the first one is. Oops.
I was just confused.
Okay. Let's try the next one. Find the number of moles of argon in 1.8 times 10 to the 24th argon atoms. So, start with what you're given. 1.8 and to the what? 24th is atoms of argon. What are you trying to find? The moles of
That's
argon.
a crazy big number.
Okay. No.
Oh, no. It's like 1 something.
So we're going to find moles. So what allows us to convert between number of particles and moles?
The Avogadro's.
Avogadro's number. Good. So what are we going to do?
Mole, 1 mole on the bottom. And then, oh, no. No, 6.0221.
6.022 to the 23rd atom on the bottom. What do you need to do that?
So atoms cancel out.
So atoms cancel out. And then 1 mole. Okay, how many significant figures should our answer have? 2. Why?
Their starting number.
Because our starting number, the 1.8, has 2 sig figs. Good. So you guys are plug this into your calculator. This type of problem where you're dividing 2 numbers in scientific notation, if you don't tell your calculator the numbers are in scientific notation, you will end up with order of operations issues. No.
The 8 rounds up to 9.
So you should get 3.0 moles of argon. Good. Okay.
I can't wait for winter break.
Okay. Let's try the next one. Determine the number of protons in 3.120 times 10 to the 24th atoms of copper. So we're given atoms of copper, right? And we're asked to find number of protons. Am I going to need to use Avogadro's number? No. I have number of atoms of copper. Yep. So on your periodic table, which you should have out, find the number. So 1 atom of copper contains 29 protons. So how am I going to work that out? Start given 3.120 times 10 to the 20. Yep. So then I'm going to put 1 atom of copper on the bottom to keep it out, and 29 protons at the top. Okay. So you guys work it out. What did we get? 9.048 times 10 to the what? 5th. Good. I want you guys to try D. We are going to go over together, but I want you guys to try setting it up, and then we'll go over together. Okay, so we're given moles of helium. So 1.500 moles of helium. And we want to know how many electrons it contains. So do I just have 1.500 atoms of helium? No. I need to figure out how many atoms of helium I have. So how am I going to do that?
Add 3.011 or 1?
What?
Well, what's the half name of the moles at 3.01 or 11?
That would, what are you trying to do in your head?
Yeah, I did it in my head. Oh, my bad.
So 1 mole of helium
6.02.
contains 6.22 times 10 to the 3rd atoms of helium. So if here I have atoms of helium. Then I want to know how many electrons are in that. So the conversion factor between atoms of helium and electrons is 1 atom of helium contains how many electrons? 2. So now I can say of helium contains 2 electrons. And then moles atoms of helium cancel out with number of electrons. So how many significant figures should my answer have?
4.
4. What do you guys get? 1.80 times 10 to the 24.
Oh, I got it. But I didn't get it at the same time.
Okay.
Because it wasn't 1, or it wasn't a single digit. It was. So I put 18. So.
Oh, that's fine. If you 18 times 10 to the 23rd. Okay. But you need 4 sig figs.
Yeah, I put 18.07.
Good. That's fine. So let's go back to dozen. So if I have a classroom and I have 1 dozen students, how many students do I have? 12. So I have 1 dozen students. How many dozen eyeballs are in that room? If everyone has the correct number of eyeballs. There's 2 dozen eyeballs, right? So we could say 12 students equals 24 eyeballs, right? Or 1 dozen students equals 1 dozen eyeballs, right? So when we talk about an atom, 1 atom of helium has 2 electrons. Do we agree? That's what they tell us, right? We can also say that 1 mole of helium, so 6.02 times 10 to the 23rd helium atoms, right? That's 1 mole of helium, contains 2 moles of electrons. Does that make sense why we could say that? Just like if we have 1 dozen students, that's 2 dozen eyeballs. 1 mole of a substance would be however many of the things that make it up, moles, right? You may find this useful. The 1 mole to number of moles is a shortcut for some of the problems we're going to look at in just a second.
Wait, but if you put 2 moles of electrons